Assalamualaikum and a very good evening to our beloved lecturer, Dr. Yani Mariana. For our presentation, the title will be Bonding and Performance Analysis of Turbine Blades and Window Panels. My group consists of four people, which is Tang Xiu Xia Sami, Ui Ziting, myself, Nurliana, and also Nuri Natasha. For my part of my presentation, I will explain the dominant types of chemical bonding present in the materials used for turbine blades and window panels, and briefly discuss how these bonds are formed. Firstly, for the turbine blade made from a nickel-based superalloy, the dominant type of bonding is metallic bonding. In this material, positively charged metal ions are surrounded by a sea of delocalized electrons. These free-moving electrons allows the atoms to stay strongly bonded while still being able to adjust under stress. Next, the second turbine blade material is the ceramic matrix composite or CMC. The dominant bonding in this material is covalent bonding, which some minor ionic character. Covalent bonding occurs when atoms share electrons forming strong and directional bonds. In CMCs, these strong bonds provide excellent thermal stability and strength at high temperatures. Moving on to window panel materials. The first material is soda lime glass, which is classified as a ceramic. This material mainly consists of covalent bonding between silicon and oxygen atoms, forming a rigid network structure. Lastly, for polymethyl methacrylate, which is a polymer, the dominant bonding types are covalent bonding and van der Waals forces. Strong covalent bonds form long polymer chains, while weak van der Waals forces hold these chains together. These weaker intermolecular forces allow the material to be lightweight, flexible, and impact resistant.
Good evening, Doctor. I am Tang Jusha Semi. Today, I will briefly explain how atomic bonding influences material properties using tubing bricks and window panels as example. First, tubing bricks operate under extreme temperature, stress, and corrosive environments. Nickel-based superalloy mainly use metallic bonding, where metal ions are surrounded by free electrons. This non-direction bonding provides high strength with good ductility along with high thermal and electrical conductivity and good corrosion resistance. These properties make them ideal for rotating tubing bricks exposed to thermal cycling and vertical. Second is ceramic matrix composites or CMCS are dominated by covalent bonding. This strong directional bond create a rigid structure with very high strength and high temperature, low electrical conductivity, and excellent oscillation resistance. Therefore, CMCS are suitable for extreme temperature tubing region. Next is window panels. Window panels focus on transparency, safety, and environmental resistance. Solar lime glass consists of a covalent silicon oxygen network with ionic modifier. This bonding results in high composite strength but brittle behavior, low thermal and electrical conductivity, and good chemical resistance. Through tempering and or lamination, it is widely used in architecture and automotive windows. Finally is PMMA is a polymer with strong covalent bonds along its chain and weak van der Waals force between chains. This gives it monomer strength, high toughness, low conductivity, and excellent corrosion resistance, making it suitable for aircraft windows and safety panels. In conclusion, bonding type directly determine material performance and application. Thank you, Doctor.
Good day, everyone. Today, I will briefly explain the pros and cons of materials used in tubing blades and window panels. First, For turbine blades, the nickel-based superalloy is widely used. Its main advantage is its ability to withstand extremely high temperatures, which is essential for jet engine operations. It also has high strength and toughness, reducing the risk of sudden failure. In addition, it provides good resistance to oxidations and corrosions and works well with thermal barrier coatings. However, this material has a high manufacturing cost, is denser, which increase weight and is difficult to machines and repair. Another turbine plate material is ceramic matrix composite, or we call it CMC. CMC offers excellent heat resistance beyond metal's limits and is much lighter, which improves fuel efficiency. It can also maintain performance at very high temperatures. Despite these advantages, CMC is more brittle than metals and its manufacturing, inspections, and repair process are complex and costly. Next, for window panels, the first materials is solder lime or laminated glass. It provides good optical transparency, has a stable structures, and a laminated layer improves safety performance. It's also resistant to weathering and corrosions. However, glass is brittle, heavier than material alternatives, and has limited impact resistance without laminations. The second window panel materials is polymethyl methacrylate, or we call it PMMA. PMMA has excellent transparency, is lighter than glass, and is commonly used in aircraft windows. It is also resistant to weathering and corrosion. Its limitations include susceptibility to cracking and limited impact resistance compared to laminated glass. Thank you.
Good evening, Doctor. I will now present the conclusion discussion for this presentation. To conclude, overall, the selection of material for turbine blades and window panels really comes down to balancing bonding type, performance, cost, and sustainability. Starting with turbine blades, nickel-based superalloy are still widely used because their strong metallic bond provides excellent strength and creep resistance at a very high temperature. However, this performance comes at a cost. The use of expensive alloy elements and complex casting process leads to high production costs and high energy consumption. While these alloys are recyclable, strict performance requirements limit how much recycled material can actually be used. On the other hand, ceramic matrix composites or CMCs have the highest initial cost and energy footprint due to advanced manufacturing processes such as CVI and PIP. That said, their strong covalent bonding, lightweight nature, and ability to operate at higher temperature significantly improve engine efficiency. So, although the initial environment impact is high, this is often justified by long-term fuel savings and improved sustainability during operation. Moving on to window panels, soda lime glass require very high temperature, melt temperature, which result in high energy usage during production. However, it offers a major advantage in terms of recyclability. The use of recycled glass reduces melting energy and makes process both economical and environmentally efficient. In comparison, PMMA, which is polymer, require lower initial energy to produce and is lightweight, which helps reduce fuel consumption, especially in transport application. However, it relies on non-renewable petrochemical resources and its recycling infrastructure is less developed, often leading to downcycling. So, to wrap up, each material involves trade-off and the final choice depends on application requirement, body behavior, recycle life, energy use, and sustainable good. Understanding this factor allows engineers to make more informed and responsible material selection. With that concluded, this presentation has come to an end. Thank you for your time, Doctor.